Intelligence analysts have a lot of information to sift through and make sense of. Our goal this year was to help them reason about the beliefs and intentions revealed by the actions they observe people taking. In previous years, we developed Insider Threat, a serious game that allowed us to collect data on how intelligence analysts work. When valuable software gets stolen from a fictional startup company, players search through a large set of emails, calendar events, server logs, and other documents to determine who stole the software and how. We then explored two methods to help analysts identify the beliefs and intentions of the fictional characters in our game. The first used machine learning to make recommendations based on the actions of previous analysts who had played our game. Its main advantage was that it didn't need to understand the documents or their context to be effective, but its main drawback was that it only works if we have examples of other analysts doing the same task well, and that's not always available in real-world situations. Our second approach used symbolic logical algorithms that reason about belief and intentions to do plan recognition. It can suggest explanations for actions analysts observe with no data, but unfortunately it requires building a bespoke, logical model of the world, including all of its characters, objects, and actions. Building this world model takes time and expertise that most analysts don't have. This year, our goal was to develop a combined model with the strengths of both approaches, by leveraging the knowledge latent in large language models like OpenAI's GPT-3 and 4.
We started by adding a summary tab to our Insider Threat game. The summary tab keeps two lists. The context list is a sequence of short sentences that are facts about the case. The events list tracks actions the analyst has observed or inferred while reading documents. The summary tab helps analysts track information they've gained, but it also acts as the foundation for a large language model's knowledge of the situation. As analysts read documents, GPT-3 automatically summarizes them to extract relevant context and events. Here, the original text of the document is shown on the left, and a list of candidate facts and events are shown on the right. The analyst can choose which ones they want to add to their summary, or write their own. After gathering some information, analysts need to make sense of what they've read and form hypotheses about missing facts or events. Consider this email from one of the company's employees asking for remote access to the company's servers while he's at a trade show. This might be an innocent request that he needs to work remotely, but it might also be an attack vector used to steal the company's software. With simple prompt engineering, we can give GPT-4 the analyst's summary of the case and ask it to speculate about motivations behind each individual event they've discovered. If analysts like the suggestion, they can add them to the new Hypothesis tab, or they can write their own hypotheses. From the Hypothesis tab, analysts can ask GPT to list which documents support or refute a particular hypothesis. The answer comes with citations to the documents GPT has automatically summarized. This is essential because while GPT usually gives pretty reasonable answers, sometimes it's downright wrong, and analysts need to be able to check its work. In general, our goal is to support analysts, not replace them.
Speculating about one event can be a helpful creativity support tool, but analysts need the ability to reason about many events at a time and how they relate to one another. In other words, they need to construct a story from the events they've discovered with any missing pieces filled in. We tried to do that via prompt engineering too, but it quickly became apparent we were going to need a more structured reasoning process.
We tried two methods for multi-event belief and intention recognition. The first was to use a large language model to translate simple natural language descriptions of events into the formal syntax needed by plan recognition algorithms. Recall that in previous years we developed an algorithm for belief and intention recognition, but its weakness was that you have to write a bespoke, formal, logical model of all the things and relationships and events in the world. We had some success with using an LLM to automatically translate an informal, natural language description of the world into the kind of syntax that we need. It's an improvement, but we think this process is still a little too onerous for most analysts to actually use.
Our second method follows the same steps as the planning algorithms we use for storytelling and plan recognition, but instead of using a formal logical model, it has a conversation with a large language model. We start with a list of events we know happened. We ask the large language model to list the preconditions that have to be true before each event can happen, and the effects each story event has on the world. Then, we start with the last event in the story, where the company's software gets stolen. and we find a way to satisfy all of that event's preconditions. Sometimes we can use the effects of existing events. Sometimes we have to invent new events to fill in missing pieces of the story. The final result is a story that integrates known events with speculation about possible unobserved events that might help analysts direct their investigations.
We learned a lot this year about what large language models can and can't do. As we suspected, LLMs aren't going to replace human analysts anytime soon. They're good at summarizing documents and extracting important bits of information. And while they're good at open-ended storytelling, once you place constraints on the content and ending of a story, LLMs really struggle. Still, we foresee LLMs being a valuable part of a larger, more structured reasoning process that can help analysts as a creativity support tool for making sense of the vast sources of information that they have to sift through every day.
Thanks for watching. This work was a joint effort between the Corgi Lab and the Narrative Intelligence Lab at the University of Kentucky. We would also like to thank the staff at the Laboratory for Analytic Sciences at North Carolina State University for their support.